Hello and welcome to another physics video. In this video we will be talking about temperature and thermal energy. By the end of this video you should be able to tell me what thermal energy is, be able to distinguish between temperature and thermal energy, be able to discuss the three types of temperature scales that we'll be working with, Kelvin, Celsius, and Fahrenheit, and then be able to take it a step further and be able to convert from Kelvin to Celsius and Celsius to Fahrenheit and vice versa. So let's get right into it. The first question is, what exactly is thermal energy? Thermal energy is simply the total amount of energy of all the molecules in a substance. And so what we know is, like, for instance, if I have a cup of water, here's a cup of water. There are water molecules in here, so there's H2O's in here, right? And basically what we know is these molecules, they're moving around, and that movement is their kinetic energy. And thermal energy measures the movement of these molecules. That's one component to it. It measures the movement of the molecules, and it measures the mass of the substance. Okay, so how much of it do you have? So thermal energy is just simply taking the total amount of kinetic energy and the amount of mass that substance has, which really in another way is looking at the potential energy of that substance. So if you have more of it and you have more movement of whatever the substance is, you've got more thermal energy. So how is thermal energy different from, say, just flat out temperature? Well, temperature is the measure of the average kinetic energy of the molecules in a substance. So if we go back to my glass of water, basically you have water molecules in this glass of water, and some of them are moving really fast. So this one's like bouncing all over the place. It's going crazy. Whereas this one here is moving relatively slow. Temperature just takes the average movement of both these molecules, and there's going to be more than just two in your cup of water, but it takes the average movement of those molecules and puts a numerical value on it, either in Kelvin, Celsius, or Fahrenheit, just depending on what scale you're using. Keep in mind that in any substance, the molecules will not all be moving at the same speed. So just because we say that, let's just pretend this glass of water is 40 degrees Fahrenheit, it does not mean that all the molecules in that glass of water are moving at the same speed. Instead, some are moving really fast, some are moving really slow. Another way to look at this is, like, you might have a class of fifth graders. And I don't know about you, but I've seen some really big fifth graders. There's some ones that are taller than me. And that's kind of unusual. But if you take the average of the class, average size of the class of fifth graders, compared to, say, the average size of a class of seniors, we would assume that a class of seniors is probably going to have a taller average height than, say, the class of fifth graders, even though there's some really short seniors too, right? So basically that's what temperature is. It's just taking a look at the average kinetic energy of the molecules in a substance. So this is just a little animation, and basically we've got these dots are supposed to represent different molecules, and the red's supposed to be hot. This kind of some shade of blue is supposed to be warm, and I guess it's kind of like a purple is cold. And if you put these molecules into motion, you can see that they're moving at different speeds, right? The red ones are bouncing around like crazy. The bluish ones are, going at an average speed, and the purple ones, they're moving relatively slow. But if we take the average movement of all these molecules, we could maybe say that the temperature of this is, well, I don't know, 35 degrees Fahrenheit. And again, I'm just making this up. But that's what temperature is, and that's how it's different from thermal energy. Thermal energy would look at the total energy of the system and give you a numerical value. Another way to look at this, and I know I'm hammering this point home, but another way to look at this, let me just change to a different pen color. Let's see here, magenta sounds pretty. Let's say I'm making a huge pot of soup. Okay, this is soup, and we'll say that this soup is, we'll say, like 150 degrees Fahrenheit. It's pretty hot. Okay, and I'll add some steam because soup steams. Okay, well I come over and I get some soup in my cup. Okay, and if I take soup from this big old vat and I put it in my cup, what's the temperature of the soup going to be in my cup? Well, we probably would all agree it's about 150 degrees Fahrenheit, right? I mean, it's not going to change that much. That's supposed to be enough. That much going from the big old vat to my cup. Let's say I accidentally trip over my dog and I spill this cup of soup on myself. Ouch, right? Well, that cup of soup won't hurt nearly as much if I spill that on me compared to, say, this huge vat of soup. Even though they're the same temperature, this one here isn't going to hurt nearly as much as, say, this one here. How come? Well, basically, the thermal energy of this cup of, or I'm sorry, this big old vat of soup is a lot more, okay? We'll just kind of keep it simple. A lot more than, say, this cup of soup, which has very little thermal energy. But they're both the same temperature. What's the difference? Well, now we're looking at the mass, right? The mass of this guy, of that little cup of soup, is very low, and the mass of this huge vat is very high, right? And so that really is another way that you can look at, like, how is temperature and thermal energy different? Well, remember, thermal energy takes in two factors. You have to think about how much mass it has and the temperature or the kinetic energy of the molecules, whereas temperature just takes an average of those kinetic energy, or the average of the kinetic energy. So we come on up to a new idea, which is called thermal equilibrium. And if you kind of just break that word down, thermal is referring to temperature, and equilibrium to me sure sounds like equal. And what it really means is that energy flows between two objects until the temperatures are the same. Okay, and here we have, like, I don't know, two aluminum squares or metal pieces, and basically this side's really hot and this side's relatively cold. And so what direction is the heat going to flow? Well, it's going to go from hot to cold. And this just kind of makes sense. I mean, if you take a cup of coffee and you leave it on your counter in your kitchen and you forget about it for like an hour or two, what's going to happen to the temperature of that cup of coffee? Well, I think we all know the temperature will drop. It's going to get cold, and it eventually will equalize out to the temperature of the room, okay? So here you can see we have two metal tiles, both at 75 degrees Celsius. You have no heat flow. How come? Well, these guys are in what's called thermal equilibrium, all right? And so no heat is flowing between these two squares. There are three temperature scales that we need to talk about. The first is the Fahrenheit scale, which basically is based on the freezing and boiling point of water. So water freezes at 32 degrees Fahrenheit in the Fahrenheit scale, and it boils at 212 degrees Fahrenheit. And this actually was the first scale to really come about. All right. The second scale that came along was the Celsius scale, and again, it's based upon water's freezing and boiling point. Water freezes in the Celsius scale at 0 degrees Celsius and boils at 100 degrees Celsius. And this scale here, the Celsius scale, is used basically everywhere in the world except primarily in the United States and a few other oddball countries. So Celsius is typically the scale that we'll use in this class, or if not Celsius, then we'll be talking about the Kelvin scale. And I should probably actually take back what I just said. The Kelvin scale is probably the one actually we'll use more than the Celsius scale. Water and the Kelvin scale freezes at 273 Kelvin. It's not in degrees, it's just 273 Kelvin. And it boils at 373 Kelvin. Okay, and you'll notice basically there's just a difference of 273 between the Celsius and Kelvin scale. And with the Kelvin scale, what it's based upon is not actually the freezing and boiling point of water, but instead this theoretical temperature that we are actually unable to achieve, and that's called absolute zero. And absolute zero basically is a point where all molecular movement stops. And this kind of gets into some things that we'll talk about later on, but let's say I have like a block of chocolate, because chocolate's delicious. And so I have some chocolate here, and we know that chocolate's made of various molecules. And even in a solid state, the molecules that it has, and I'll just draw those with little circles, even though they're not freely flowing and moving, they are actually vibrating. Okay? And I'll make my little vibration marks. Okay? That little bit of vibration there is actually kinetic energy. What absolute zero actually means is that if you can get this chocolate bar cold enough, you would actually have no movement. Or another way of saying that is no kinetic energy, which I'll abbreviate with KE. And that's significant, and it's a point that we have not actually achieved. Even in outer space, space has a temperature of about 2 Kelvin. So even in outer space, we haven't achieved absolute zero. Now, is that to say it doesn't exist anywhere in the universe? Well, that's impossible to say at this point, but that's basically what the Kelvin scale is based upon, is that there are no negative numbers in the Kelvin scale. Now, what is the tool used to measure temperature? Well, I assume you guys know all that. That's something called a thermometer. And if you kind of think of thermometers like speedometers, it's not actually a bad analogy. When you drive in your car and you want to make sure you aren't speeding so you don't get pulled over by like Officer Friendly, basically the speedometer tells you your rate of movement in your car. A thermometer does something very similar. Basically, a thermometer, if I draw a thermometer here, a thermometer measures how many little particles, if this is a particle, are running into this bulb down here. And that when it hits this bulb, it basically is transferring energy and makes in thermometers nowadays, it's alcohol, the alcohol rise up, and then it gives you a measurement in terms of temperature. Okay, so thermometers are very much like speedometers in that they're measuring the kinetic energy or the movement of the molecules in a substance, whether it's a solid, liquid, or a gas. And if you're just looking for a fun weekend experiment, especially in the cold winter, fill a balloon inside your house and then put it outside and you will see the balloon shrink. Or on the flip side, fill a balloon in the summer and let it bake in the sun for a while and the balloon will expand. How come? Well, basically you're transferring heat energy to those air molecules in the balloon and it causes it to expand if it gets warmed up, shrink if it gets cooled down. And the same thing happens to your car for those of you who drive. In the wintertime, typically my check air pressure light goes on for my tires. And it's not that like I ran over a nail or some sort of object and punctured my tires. Instead, what it is, it's gotten so cold outside that the air pressure in my tires has dropped to a point where my check air pressure light goes on. And so typically you'll see people at gas stations and such filling their tires because basically it's gotten cold outside and now the tire pressure has dropped to a point where like their tires are actually a little low. This is a video from Steve Spangler, and he basically takes liquid nitrogen, which is nitrogen in the liquid state, and it's very cold, and he sticks a balloon in it, and he's able to make his breath change from a gas to a liquid because of the temperature drop. And it's kind of cool. You can see the balloon shrink and do all this stuff. So take a look at this video and we'll get back together in just a second.
Yeah. All right, so watch what happens if you watch very, very closely. As we submerge it, this is exactly what happens with the tire, but really on a much easier level, a slower level. The molecules, when they get cold, start to contract. The molecules get closer and closer together. So this is a really dramatic representation, but take a look at this. I'm going to turn my breath into a liquid. So as we push it down, we get it closer and closer. Pull out that flashlight and turn it on, and we're going to hold it up, and we're actually going to see, you can see that my breath is turned into a liquid. Look right there at the bottom. Can you kind of see how my breath at the very bottom there is turned into a liquid? Isn't that amazing? And so now watch, when it starts to warm back up again, look what's happening. It's getting warmer and warmer. And it's coming back exactly the way that it started.
Okay, so again, that's kind of a dramatic representation of what would happen to your tires in the winter. I mean, obviously it doesn't shrink that much, but that cold temperature causes the molecules to contract down and eventually actually change states in this case. So his air actually changed from a gas to a liquid. These are some important formulas, and this will be something you'll need to be able to use for various assignments in class. These are ways that you can convert between Fahrenheit to Celsius and Celsius to Kelvin. Okay? So if you know Celsius, all you have to do, if you know your Celsius temperature I should say, all you have to do is use this formula to convert your temperature to Fahrenheit. And so you just take 1.8 times your degrees Celsius temperature plus 32, and it's just basically a calculator problem. If you know Fahrenheit and want to get it into Celsius, you're going to take your Fahrenheit temperature, minus it by 32 degrees, and then divide that by 1.8. And then if you want to get into Kelvin, it's much easier. You take your, if you want to get into Celsius from Kelvin, all you have to do is take your Kelvin temperature and minus it by 273.15, and that gets you degrees Celsius. And if you want to get it into Kelvin from Celsius, you just use your Celsius temperature and add 273.15. You'll notice basically Celsius is kind of the gateway to go from Fahrenheit to Kelvin. So you need to take your Fahrenheit temperature, turn it into Celsius, and then your Celsius temperature, turn it into Kelvin, and vice versa. Okay, that takes care of this video. I will see you guys next time.